very much. I really enjoy this advance applause. It's different from most conferences. In most other conferences, you first have to deliver a good session, and then you might get some applause. So I really appreciate your advance feedback. I hope I can live up to this. In the next, in the next 75 minutes, well, we're going to talk about parallel programming. It's not really multi-threading the way we know it, but it's about taking advantage of the number of cores your machine has for regular applications. Now, the interesting thing is, the topic of today morning, the HTML5 topic, is actually on the totally opposite scale in terms of parallel programming. Any browser which is available today runs on a single thread, which is what makes JavaScript so easy, so you don't run into cross-threading issues, etc. Even the upcoming web workers will allow transparent marshalling back to UI thread. So it's quite interesting for me to talk about HTML5 in the morning and about a very, very different view of the world in the afternoon. Okay, so as always, the slides and the samples are available at weblogs.thinktexture.com/Ingo. I've uploaded the slides and the samples just 10 minutes ago before the session. If you've got any questions, I'll be around afterwards, of course, and you can always send me an email to ingo.rammer@thinktexture.com. So, why are we here today? Well, the thing is, I took a few screenshots of a few different machines I've got at home. That's the lowest end machine I could find at home. I don't have a netbook right now, so the lowest end was a 2-core machine. This is a notebook computer I used to use until about 2 months ago. It has 4 cores in a notebook. That's a 2-kilogram computer, or less, it's 1.5 kilograms. It's a ThinkPad X series. It has 4-core CPU, or actually 2 cores plus hyperthreading. My current notebook has 8 threads. It has 4 cores, each being hyperthreaded. So that's what you can get today, that's current hardware. Now, a friend of mine has an even better machine. And the thing is, this is for real. Now, unfortunately, I personally don't have access to a machine like this, but some of our clients do. That's the interesting thing. I've been talking about parallelism for about 2 or 3 years now, and I've used the same screenshot, the last screenshot throughout the times. Now, 2 or 3 years ago, thinking about a 128-core machine was totally out of the reach for most companies. But today, we do have clients, regular clients, hosting web stuff on machines which are equally powerful as this one. That's the impressive thing. So multi-cores are really, well, that's the standard. I couldn't even get a single core. You know, today, if you buy any phone from non-Microsoft, as of today, if you look at the top-of-the-line Android phones, they are dual-core phones. So even on a phone, you get dual cores. Windows Phone 7 will get dual cores as well, etc. Okay. That's important, because the future brings us, quite likely, more cores at lower speed. The reason for lower speed is that this allows you to reduce heat generation and power consumption. So if you look at large-scale data centers, you'd usually see lower speeds. You don't see 3.6 gigahertz CPUs in 128 core machines, but these are lower speed CPUs. Otherwise, the heat density would be way too high. You couldn't move the heat. You would even be hard pressed to even find the power to supply these racks if they would be 3.6 gigahertz CPUs. Actually, today, if you look at a data center, the problem is not cooling anymore. The problem is actually turned to be providing power. And a lot of data centers are currently limiting the amount of cores you can put in onto 1 square meter, into 1 rack, so that they can provide enough power and enough cooling at the same time. Okay. So the next question is, what does this whole parallelism mean? Is this the multi-threading we have known for years? You know, multi-threading is used in different ways, of course, right? At the end of parallelism, at the lowest common base of the whole parallelism movement you see here is, of course, regular multi-threading supported by your operating system and by your processors. But what we are talking about here, or what we are thinking about when we talk about parallelism, is a lot more than your regular multi-threading. If you look at multi-threading as it's done in most applications, what it does is it decouples the user interface thread from some background processing. It's actually just a decoupling. It's achieving some kind of asynchronicity so that your UI can be refreshed and can remain responsive. That's not the kind of parallelism I'm going to talk about in this session, because it does not really parallelize your work. Just by moving your work off the main thread, well, it still means that your work is still single-threaded. It's just not blocking the main thread, so it really doesn't change too much. What do you need instead to achieve real parallelism of your work? Well, first you need to think about how to partition your work, because you can't just take your random algorithm X, which manipulates data in memory, and say, okay, I'm running this on 128 cores now without any changes. So you have to find a way to partition your work, which means that somebody has to find a way to manage the queues of small pieces of work which you want to have partitioned, and you need to find some way to synchronize this. Today, what we still see is most applications use the .NET 3.5 and smaller paradigms of manually using threads and manually using the thread pool. The problem is that the thread pool doesn't give you the synchronization APIs which you'd like to use just for parallelism. It gives you synchronization capabilities using the standard Windows synchronization, using semaphores, auto reset events, manual reset events, etc. But you have to go very deep. You have to understand how Windows thinks about synchronization constructs. This might or might not be what you want to do. In general, it's not what I see most developers want to do. The next problem, and I'm just going to show you a few slides, and then I'll spend the rest in code mode. Now, the important problem here is that the thread is a unit of scheduling in the operating system. It's not a unit of work in your algorithm. If you process 10,000 items in your algorithm, you cannot start 10,000 threads. That's not the idea behind this. So that's how the thread pool came along and similar things. It's just that a thread can never match your unit of work. In fact, if it does today, if you are creating any kind of software where one thread matches one unit of work, whatever the unit of work is, then you should quite likely spend some time to optimize this. We've seen this quite often in the past in, let's say, socket-based communication, TCP/IP sockets, when every single connection would spawn off a new thread. And things don't work like this. If you take a thread, every single thread takes 2 megabytes of uncommitted virtual memory. So that's the easiest way to run into out-of-memory situations is by just creating too many threads in your application. It's just not meant to be used this way. If you're running CPU-bound, if you do real CPU calculation operations, then you should scale your number of threads to actually match more or less the number of cores. You have to add a little bit of overhead, of course, or a little bit of a small number of additional threads to handle the enqueuing and dequeuing overhead. But apart from this, usually what you want is one thread per core, if you are CPU bound. If you are IO bound, if your code communicates to an external system, what you want to do to achieve best possible scalability is to run your code asynchronously. You don't want to block a thread just because you're waiting for a web service. That's why begin invoke and end invoke has been created in the .NET framework starting from version 1. Because this allows you to take your I.O. request, move it into some kind of I.O. completion pipeline, and have Windows call you back as soon as the operation is completed, so you're not blocking a thread. Okay, but that's an aside. I.O. bound is the kind of things I'm not going to talk about. Today I'm going to talk about CPU bound, about parallelizing your CPU bound loads. And .NET 4 gives you a number of things for this, and there are even more constructs for this coming in the future, which are available today as CTP, but even what's there today in .NET 4 is pretty massive compared to what's been there before. What you'll get in .NET 4 is you get very fine-grained parallelism. You get a unit of work scheduling, not the thread-based scheduling, but now you get unit of work-based. You can use smaller items and put them onto a queue, and they will be executed by a thread pool at the end of the day. You will get a number of coordination data structures, blocking queues and similar things, constructs which you can use to communicate between two different threads if you need to do this manually. You will get structured parallelism using the parallel keyword or the parallel class or type at the end of the day. And you get declarative parallelism by taking a link expression and moving it into a parallel space in a very easy way. Underneath all of this, Microsoft has implemented a number of optimizations to a thread pool, which includes optimizations for locality, optimizations for reducing the number of locks, but I'm going to talk about these later on. Okay, so the rest of the slide deck, the biggest part of the rest of the slide deck is a reference deck. In this slide deck, you'll find all the things I'm going to show you here. And of course, as I said, you can download these samples. But let's switch over to Visual Studio. I'm going to show you the application we are going to talk about during the rest of the session. Now, that's very simple. This is a grid of, I don't know, it might be something like 40 by 40 items or so, or 40 by 25 items. But the important thing here is that this represents something which you want to process. So right now, when you're starting, it's processed, this data is processed serially. And every single processing step takes quite a while. And this quite a while is not a thread.sleep, but that's a spin wait. So it's really spinning the CPU while it's waiting. Now the problem is, let's look at the code. So the first step is very easy. The first version is I'll just explain the demo infrastructure first. So what you'll get is there is one button start click. That's a very simple application. Basically, you get two buttons, one for canceling for later and one for starting the task. I create an array of 1,000 elements which will be processed, and I'll pass this to one of those demo methods. I think there are about 16 different ways of looking at this. And inside of a demo, I'll process these items. I'll do various things. So the input data here is always this list of 10,000 items, which are represented by the item on the user interface. Processing itself means running a spin wait for a certain amount of CPU cycles, just really doing something on the CPU. The visualization, when you see that when the red square goes over the screen so that you can see how many threads are concurrently being, or how many items are concurrently being processed, is not affecting the performance you're seeing here. This is done on a separate thread. The whole visualization is done on a separate thread. Every single processing step here on the data side just sets a flag in a global array. And the visualizing thread will read over the array and will visualize this, I think, in every 100 milliseconds or something. So that's important. What you see here is real performance. The visualization has no effect on it, or hardly any. Okay. Again, if I run this, and we'll get some timing information at the end. We have to wait, of course. The problem is I really can't make it faster because otherwise it will be too fast for the later tests. So right now, it's taking us 6.2 seconds to process all these items. The interesting thing here is, if we look at Task Manager, and that's actually the critical thing here, and let me just try to, oops, this was the wrong shortcut. Let me just try to move this so that we can, let me just arrange this, so that you can follow along here. Okay. So now we are running at 1% CPU. I've not started the application, one or two. So it's pretty close to zero. We have some peaks in here. So I click Start, and it's processing now, and we get between 10–20% of CPU usage out of this. Now the problem is, this is an 8-core machine, so getting 10 or 20% of CPU usage out of this big machine is really not very effective. But of course, that's actually what has to happen, because it's a single-threaded application. A single-threaded application means it can run by definition on only one core at any time. Okay, so now the naive implementation, the naive solution would be to say, okay, I'm showing you the very wrong thing first. The very, very wrong thing, which you have to forget immediately after seeing it. That's important. I mean, you cannot go home and tell anybody that I've shown you this. We have to be very clear about this. This would be thread T is new thread, and we'll pass in a parameterized thread start, and we say we cast this to demo data P. Oh, no, I don't want help. I definitely don't want help. No. No, I really don't want help. It's fine. You know, I'm just glad that at some point in time, Microsoft must have changed this, because in the past, when you hit F1 and you didn't want to, it would actually freeze Visual Studio and you'd have to wait for help to start. I was just glad that this was changed now. The interesting thing is, I've had this notebook only for about 2 months now, and in the past, or IBM, it's a Lenovo notebook, and the ThinkPads have a configuration utility, or have had one, where you could actually enable a delay on F1, so you'd have to press it for 3 seconds before it's triggered. This was perfect. I forgot to install this on this machine. That's why you've seen it. Okay, so we are starting threads now. T.start, and we pass in the element. Well, let's see if this is a good idea. The interesting thing is, right now, quite likely the application will not crash. So let's see, yeah. It's not really fast. It does something in parallel. You can see there's more than one square red. That's the one which is currently being processed. We get 5.2 milliseconds, which is actually quite surprising, because if you would run this particular piece of code on any real application in which the processing would take a while, in which this would not be as fast as it is in my application, but let's say if this would take 100 times as long, then the threads would not be able to finish before all the threads were started, and you would immediately run into an out-of-memory condition. Your application would crash. Windows would give you Windows error reporting, and the application would be done. So that's not really a good idea. It's just, we're just glad that we don't have time to start this many threads in reality, because the process here is too fast. Now the next option, and this is actually a pretty good option, is if you don't need any control over the outcome of your computation, you can do thread pool, queue user work item, and actually I could undo this, because I could just, instead of running this, I could say thread pool, queue user work item, comma p, comma lm, and remove that part. This would now this would now use the standard .NET thread pool to queue the items. And let's start this one. And whoops, there we go. Yeah, it's noticeably faster. The problem is it doesn't give me synchronization constructs. So the timer doesn't, the application doesn't wait for all these items to be processed. Instead, it just, of course, it just continues. I've just queued something onto the thread pool, and my application continues. It doesn't wait. So the next thing, if we wouldn't have the parallel framework or the TPL, would be to implement something here to wait for the completion of all these threads. And that's where the thread pool is extremely limiting, because you don't have a wait one or wait all on the thread pool. You know, potentially, you can't also just say, well, I'm waiting for the last item, because the thread pool doesn't give you execution guarantee. In fact, if the second to last item would take 5 seconds to complete, and the last item would complete pretty quickly, then, well, you might continue too early. And that's the critical thing. So the thread pool is nice if you want to take something and fire or forget it to somewhere else. Okay, and I'll just rebuild the original view of this and move on to the next one. So let's go to a parallel world. Now, in a parallel world, the first thing we will see is parallel.forEach. So instead of running a regular for each, you can now in .NET 4 run parallel.forEach. You pass in a list and you pass in a lambda expression or any delegate, any action, which should be executed, and the system parallelizes this work for you. That's very interesting, because the code looks very similar to the regular for each. It's still just for each. You just take this inner element and put it in here. Okay, so if we run this, we're getting exactly what we need for most cases. So let's just run this. We get perfect parallelization. The framework analyzes the number of cores I have in my machine, starts as many parallel tasks as it finds cores, and everything is okay. Let's look at the bottom of this screen. Oh no, that's only on the next one. So it just takes the input set, splits it in the number of cores, and starts to process the individual values. That's a very simple API. It gives us the immediate speed boost here, which was expected. We are going down from 6 seconds to 1.3, so it doesn't scale linearly. The reason is that these are hyper-threaded cores, and a hyper-threaded core, has more synchronization overhead between those two threads per core than a real separate core would have. But it gives us a lot of speed gain in a very, very simple way. So this would be easy if you don't need to wait for any response, or if you don't really process anything. You just need to process a number of items in an easy way, and that's it for you for now. Okay. The next possibility would be to use the tasks API. Now I'm telling you about this whole demo 1, 2, 3, 4, 5, 6, 7 thing. In the past, I used to do this session as a live coding session. I was just typing the code in here. And at some point in time, I realized that, typing code here might be fun for me. It might be fun to watch this whole typing going on here. But the problem was, if you would download the source code later on, I would have changed it all the time, so you would only get the latest version. So I decided to go this route instead, to walk with pre-canned demos, which is not normally what I do. Okay, but in this case, we have them pre-canned. So in the third version, I'm using the task API. The task is something which represents a unit of work, a unit of, work which can be scheduled onto the TPL framework. This is really just the smallest unit of work which you can use to parallelize your algorithm. This has nothing to do with threads. If I run this on a single core machine, and if I create 1,000 tasks on a single core machine, they will execute on a single thread. If I do this on a dual core machine, these tasks will be executed on 2 threads. So that's important. We have a layer of abstraction between our work and the underlying CPU architecture. Now, creation of a task is very similar to the creation of a thread. It's just, you pass in a lambda expression of what you want to execute for each task, and you pass in the parameter which you want to execute on. And then you start a task. And right now, these tasks will just be started. Nobody's going to wait for them. So let's just run this for now. And I'm going to talk about this interesting thing which is happening here in just a second. But just watch it again. So we have one which runs backwards, and we have a number of them which run forward. That's pretty interesting. When I've seen this for the first time, I needed to actually talk to someone from this team to find out what's happening here. And that's pretty interesting, because what they are doing is, this is a locality-based optimization. They are basically saying that, we are going to run not the thing which you enqueued. It's not FIFO, it's actually LIFO. It's last in, first out on one of the cores. So one of the cores runs LIFO, because the assumption is that if you run the thing which you enqueued last, if you run this for the first time, the chances are high that the data you're using is still in your CPU's thread, in your CPU's cache. So that's the idea here. And they're only running this on one because they're figuring that, for the rest, it will be okay. That's just a default scheduler. These are things which can be changed. So there are a number of samples when you download the sample or the help package to the TPL. You'll find that there are samples for custom schedulers. But a default scheduler will do a locality-based optimization. And that's why it runs backwards on one of them. But still, the important thing here is you are scheduling tasks, and they might continue to run or might start to run at some point in time later. But you really schedule a task, and this has nothing to do with threads. The system will decide how many threads it will actually create for you. Okay. Next step is what happens if you actually need to wait for a task. So you need to wait for this whole package, because right now, the complete package, all the tasks are executed in a fire and forget way in the background, just like thread pool queue user work item. So let me go back to here and move this to demo number 4. And if we want to wait for tasks, you can do imperative things like tasks.waitAll, or to wait for all tasks in a certain array. Or you could do task.waitAny to wait for any task to complete. If you have multiple tasks in an array, you can wait for any of them to complete. And this does exactly what the name lets you think. So if we run this, it will do the same thing. But now we get correct timing again. So now we are at 1400 milliseconds. Of course, there's some kind of fluctuation here depending on the utilization of my machine in the background. but we get the same pattern, it's executed in the same way, and it's still, yeah, it's nearly fire and forget. We don't get a response value, we don't calculate anything. It's really just running in the background. That's the easiest, that's an easy way to run things in the background. The next thing you could do with tasks is to create relationships. Now, in a relationship, you can say, well, I create a parent task and child tasks. So in my case here, I create a parent task, an outer task, and inside of my parent task, the content of my parent task is the creation of additional tasks. And when I create them, I pass an additional option, a task creation option, and one of them is attached to parent, which means that the parent's lifetime is controlled by the lifetime of all childs. As soon as the childs have completed, will the parent task automatically complete. So what I'm doing here is I just call parent task.wait. And the reason for this sleep 100 is that I'm going to show you debugging tools for tasks and threading. But these tasks, they are started delayed in the infrastructure. The infrastructure will delay the creation of these tasks, and we need to wait for just a tiny bit before I can show you this in the debugger. For a real code, the sleep would not be necessary. Okay, but now we're creating one task which has 1,000 small subtasks inside, and we're waiting for these 1,000 small subtasks. No, we are not, because I need to change this, of course. And we are now running this one. Okay. So we are breaking here, and there are new debugging tools for these kind of things, for whole multi-threaded debugging. You will see that there is, in debug windows, there are two more options in Studio 2010 for .NET 4 applications. You have parallel tasks, and you have parallel stacks. And parallel tasks show you the current situation of tasks, or the current running or scheduled tasks, etc. So you can click on it to get position information, just like when clicking on a thread, it would show you which source line is executed. And here we see that we have 2, 4, 6 tasks which are currently running. So for whatever reason, the scheduler has decided that 6 tasks would be perfect for my system at this point in time. The scheduler might adjust this over time. There is one which is waiting, which would be the parent's task. And there are a number of them which are scheduled. Actually, the system even tells us that we have scheduled more than it's going to show us. So all these tasks, they are scheduled in advance and will be executed later on. That's something which is also very important. You can cancel scheduled tasks again, and you can define relationships between tasks. And so when we talk about relationship, well, the first relationship is the one you're seeing here. That's a parent-child relationship. And I put myself a message box in here because I've added a new demo quite recently, which I didn't want to renumber all my demos, so I called it 5A. But the problem is if I just continue running this with you, then I might forget 5A. So I decided that I have to put in a message box here. That's a major, major hack. You know what? The reason for this major hack is that I forgot my roots. I didn't start, but I did some basic programming in my life. And in basic, those of you who have done basic programming, you know things like line numbers. You do 10, print foo, 20, go to 10. The reason we used 10-based numbering is so that somebody could later come along and do 15, print bar. And I forgot about these roots. I just really numbered the demos and didn't leave any spaces in between. But then I said, well, there's a new demo which I'd like to show. And I decided to just keep the numbering the way it is. Okay, so we're running this one again. It's executing. Our parent task is completing. We need to remove this message box again, otherwise we don't get nice timing. And we're running this. We should get about the similar timing. Yeah, we get about 1,400 milliseconds for the whole processing. And now the next demo, 5A, the one I've mentioned in my message box, does something interesting. Because up to here, you could somehow fake your way through by using the thread pool and some auto-reset events, and things could work out. Or you could just increment a counter and use one auto-reset event if the counter reaches the maximum number, etc. But what you have here is now a very interesting feature of tasks. And the tasks, as they are here today, are created for CPU-bound operations, but in the future there are let's say, I/O-bound operations which will return tasks to you, and you can then use these tasks to kick other things off. So there's a whole async framework coming in the future of the .NET framework, which will include a lot more infrastructure built on top of tasks. And that's when you will see a lot of those things which are used in this method to be quite valuable in your day-to-day use. Okay, so what I'm doing here is I'm creating 3 different tasks. I create one task, and all of them process a third of all the items, because I have 3 of them. So I create one task, which, well, first, it's a task of int. I haven't talked about this before, so let me just introduce the task of t first. A task of int is a task which will return an int. So if we go there and say task of int t is task.factory, start new, and we just say return whatever, return some kind of number. And oops, t is defined already somewhere. T2, no, T2 is also defined test. And we'll return a number. And the interesting thing about a task of t is that you can access its result. So I can say var foo equals test.result. And I can say messagebox.show result is foo. Now this would be easy. Of course, we wouldn't normally start a task just to return a particular number. But let's just run this to make sure that we are in the right demo. Let me just check if I move to 5a. Okay. Now, we're running this one. We see, okay, result is 1,000. That's exactly what we would have expected anyway. Okay. Now, if your background task suddenly starts to do something which takes a little longer. Let's do a sleep here. We don't need a spin wait. But let's say our task sleeps for 5 seconds. Then I could do the following. I can just continue running here. Message box show still running. And now one of 2 interesting things could happen when I call .result. I can click OK, and it tells me that it's still running, and we know that it's going to take 5 seconds, and right now I'm talking for longer than 5 seconds. I click OK, and I have my result. Everything's OK. But the interesting thing is, if the first part is actually faster than the task, so I click OK, and then it's blocking. The task automatically blocks on your call to .result, waits for the task's completion. That's pretty massive, because for a lot of parallel interactions, for a lot of very simple interactions, this allows you to decouple back-end logic or background logic from your main logic, and you still get very easy synchronization points. You just define a task of something, and you access .results when you need it, but in the meantime, you can do other things, kick off more tasks, do primary thread work, etc. That's pretty simple. Okay, so that's your task of int. In the past, long ago, this was called a future of int. And in other programming languages, this is called a future of something, because it is a future value. It doesn't have a value right now, but if you access .result, it will block until it gets a value. Okay, well, we can get rid of that part and look at the one we are really interested in. So in my case, I'm creating 3 different tasks. And these tasks, they process something. So they do the same, they call the same process method. Process actually returns a value. And in my case, I'm summing up these values. But it's just random so that I can show you that it can deal with return values. I could run this one. I could add a return statement here, and I could just do messagebox.show result is sum. No, result is, of course, t.result. And if I run this, then it will process the first third of elements. It processes them backwards and will give us the sum of whatever processing happened in here. Okay. Now, the interesting thing is I can now combine tasks. I can now specify that I want to run a second task after the first one has completed. To do this, I don't use the task factory like here, task.factory.start new, but instead I used some existing task object and I specified continue with. So I say, well, this is the first task, and continue with this task after you have completed your work. It does another sum of another third of these items. In my case, it shows a value, but it could also simply just return the value. And the important thing here is we say, well, execute this part only if the first part has been completed successfully. So in this case, I could just use the same code as before, but call the code on T2, and the whole system will wait till T2 actually gets a value. So let's run this one again. And I'm running, it's doing the first task, and now it's running the second task, because the first one has been completed successfully. Okay, but the interesting thing is, it's of course, well, given that there is a only ran to completion, only on ran to completion parameter here, you can imagine that there are other parameters as well. So I can define error handling code in a very similar way. And I do this by defining another task. And this would be task 3, which also continues from the first task, but this time with only on faulted. So I can create a chain of execution. I say, well, execute this, and then if everything's okay, do that. Otherwise, do this other thing. And I'll move a message box in here so that we can see this. What's in here? Oh, we don't need this one. We can actually get rid of that. And so we just have our 3 tasks for now. And this one is now only on faulted, only if it's going wrong. If the first one went wrong. So I'll start the process, I'll remove my breakpoint, and same thing. First thing processes, second thing processes, and after this we are done, everything's okay. I've removed the message box for now. Now, if my first task would throw an exception somewhere in between, in my case, I'll allow it to do some kind of a bit of processing, half of it or whatever, and then throw an exception. And now the second task will be triggered. And it goes ahead, it does something. Well, it shows me the exception in Visual Studio. I just hit continue, and it runs this third task, and it gives me the message box at the end of the third task. Now, that's the interesting thing here. You can set up chains of tasks, and then you kick off one, and it does the automatic error handling for you. That's important when you can imagine that, let's say, a web service call or a database call doesn't provide you a method. Let's just assume something. Let's just assume that you have a method today which says public customer load customer int ID. And this goes to a database and returns a custom object to you. Now, today, when you're using this, you would use it something like customer cust equals customer equals whatever, load customer 1, 2, 3, 4. And you can imagine that there's some more code you need to look up the customer's address information or the customer's invoices. So you would say invoices or you'd say list of invoices is load invoices for 1, 2, 3, 4, etc., etc. Now, today you would execute this code synchronously if you'd run code step by step, of course. And you can imagine that you can design your API so it doesn't return customer, but it returns task of customer. And in here, you would create a task of customer, and T is task.factory, etc., etc. And you pass in your Lambda expression to do your actual loading, and you simply return this task. And in your API, you would now not directly access the customer, but this would be your customer task. You could do the same thing for your invoice task. And you do some more processing, and only when you need to actually display the information, let's say if you're on a web page, only when you display the information would you go ahead and do task.result. But now, of course, the important thing is, given that all these things run in background, you need to have some way to do exception handling, because you can't do a try-catch anymore. If you do try-catch, exception EX, then the exception won't happen up here, but the exception will actually happen in the line when you access.result. So that's one thing. You can do try-catch exception handling as you always did, or you can say, well, you define yourself an exception handling task and let this task continue with the exception handling task in case of failure. Might not be the most obvious API today, but I think we're going to see more and more of these kinds of APIs, of asynchronous APIs. If you are creating JavaScript code, for example, that's a very natural way to do things. In JavaScript is by definition asynchronous, even though it uses only one thread, but every I/O operation is asynchronous, which means that you always pass in callback methods for success and a callback method for failure to continue your execution. Okay. So we can keep this code for now, and let's go to another sample. Let's look at a different way how we could process this data. So let me just collapse this one and start demo 6. Now demo 6 is now using in-memory link to do things. Now in this case, I'm adding filtering. I'm basically saying, you know what? I want to filter and output. Until now, we have only used process. But now I'm just saying, you know what? I want to process, but I want to check the result of this process method. And if it is above 500, some arbitrary value, if it fulfills some arbitrary condition, then output this element. And I'm going to show you this in a second. And let's just run. Okay. So now it's processing, and now the values are above 500, so it's starting to output. Output in this case is color the thing yellow. That's linked to objects. I'm using a where clause on link to objects. Everything's easy, no parallelism or anything. I can start this, it's running synchronously, single core, it takes ages again, just like our first sample did, but it's highly sequential, of course. Okay. Now, I can use parallel link instead of regular link, which would mean that I just convert this one into that one. I just need to add the sParallel command here, or method here, which converts any link I enumerable into a parallel expression. And that's massively powerful. So let's just switch my active demo to number 7. And now we have a parallel link. So the statement here is still the same. It's still where p lambda process is greater than 500. The only difference is sParallel. And let's run this. And let's start. So now it's running this code in parallel, and this might or might not be what you expected it. Now this is now changing your algorithm. If your algorithm depends on the sequence of items in output, let's say if output would take items and put it into another list, and you would normally expect the list to be sorted, then right now it's not sorted anymore because the execution here is in a parallel way. It's not deterministic for you. It depends on my number of cores, the number of cores I have in my machine. But you know, it's not sequential. And there are things or ways how you have and can change this. Now, there's one thing I'd like to show you. I can start Task Manager, and I'll change the CPU binding for this application. This would be visualization demo, and I'll go to the affinity mask. And right now, the affinity, this application uses the default affinity mask. So it runs on all CPUs. And now I'm moving this to only run on, say, CPU 1. So now I'm changing the affinity mask to only give it one CPU. I click OK. And I hit start again. And now it's still doing some kind of parallelism. It's still trying to do some parallel logic, but of course it can't, because even though it detects that my machine has 8 cores, it only gets one of them. So now the execution takes longer, and it looks even more random. But that's what could happen. So your algorithm cannot depend on any kind of sequence, etc. It totally depends on the setup of the machine, if you don't do anything special. So let me change this again, so that we have full affinity again. And yeah, we have it. I'm feeling better now. You know, I paid for 8 cores. I really want to use all 8. Okay. Let's go to the next one. So before we going into buffering or ordering this, parallel link gives you one interesting thing. It allows you to cancel operations. So let me move this one to the current one. And cancellation is a 2-step process. So cancellation by default just means that, you know what, you can take this link, this parallel link statement, and there is a way that you can cancel this right in between at some point in time. Your user can cancel this operation consisting of 1,000 elements. This is based on a cancellation source. The cancellation source is something you create, and the cancellation source gives you a cancellation token. And in here I have a cancel button, so I'm just going to show you the code for a button cancel click. When the user clicks cancel, you go to your cancellation source and call cancel on it. And as you've seen, the cancellation source gives you a token, and you can take this token and use it inside of the task and the parallel framework for a number of different things. You can pass this to a parallel link, you can pass this to a task, you can use this to cancel a whole lot of things with one cancellation operation. All the things which are currently running will be canceled. Of course, there is no thread abort or something like this, so your small task, every individual task which is currently being executed will run to its end, but then no more tasks will be scheduled. All the scheduled tasks which have the same cancellation token will immediately complete without doing their work. Okay, so let's go back. And this was somewhere in the area of demo 8. Okay. So in here, this is just UI code. I just need to enable the cancellation button for this particular test. And then you again say list.sParallel. That's the keyword here. And then you can pass various options. And with cancellation is the first one I'd like to talk about. With cancellation gives you cancellation support. You just say with cancellation, pass in your token. The rest of the code is exactly the same as before. And let's run this one. If you run it regularly, everything works exactly the way it did before. But I can now hit cancel, and the operation will just stop. The delay you've seen here is just a delay in the visualization, because my visualization runs asynchronously compared to the actual operation, but you can cancel this. Then, of course, you get partial output depending on how much has been processed or not. But the easy thing is that you can give your user an option to cancel your algorithm. That's a lot harder if you do manual scheduling and if you do manual multi-threading and manual separation of your work onto multiple threads, because here you have to use quite complex synchronization constructs to allow a clean shutdown of your work queue. Okay. And so we can do canceling. We can order the results. Because the problem is, right now it's, as you've seen, we get random results. So the results are in any kind of sequence. In this case, if you need ordering, you can add the asOrdered method. And this always changes the way how this statement is set up. So I run this with ordering now. And the first processing looks the same. So the interesting thing is it processes them, the real link operation, the where clause, this part. The where clause is still run in parallel. Of course, that's the reason why we did it. We can't serialize this because we don't want it to be serialized. We want this to run as fast as possible. But then the output is held back up to the time when you could perform sequential output. And looks like this. So we are waiting. Now we can do sequential output, and then it starts to output. It has not finished. You see that at the end there are still some items open while it's running. I'm going to show you in a second again. But you have to watch this space. It starts the output phase before it has completed the initial where clause. So I start this, and now I get yellow, but the last core is still operating on the last set of data. This is an optimization. It wouldn't be reasonable to buffer this for longer than necessary. But now it's getting to be interesting, because if you have to do this manually today, you have to set up a queue of work, multiple readers on one queue, and then you have to set up a destination queue or whatever, but you have to use interim queue, which will be used for the time when you cannot really fill the queue in the sequence you need. That's quite an interesting problem if you have to solve it manually. And I think it's pretty massive that it's enough here to just say as ordered. I need the result ordered. That's it. And you'll get it ordered. Okay, then there are a number of buffering operations or merge options. So, and again, that's how you can define how you want to get your result in terms of again, waiting for certain items to be ready. Let me move this one to the current sample. And let's run this one again. Okay. Now we get buffering. Now all the threads complete their work before any thread starts the outputting of their work. That's now fully buffered. So in this case, we just say, you know what? We don't want to run the first part before everything has finished. Again, your algorithm can demand this. or maybe not, but that's something which totally depends on your algorithm. That's something which we cannot, or the framework cannot decide for you. But it's again, the thing is, you can specify that you want some kind of merge option. Fully buffered means you have to wait for the end. There are different buffering options, which would give you interim results in between. I think that today, actually, everything but fully buffered means no buffering. So auto buffered means no buffering, default means no buffering, and not buffered means no buffering. So they are somehow intended for future use. But today you can say fully buffered or no buffering, essentially. And you can specify a degree of parallelism. You can say, well, I know that I have 8 cores, but actually I need to do something else in the background, so please don't use all the 8, use only 2. You specify with degree of parallelism 2, and you'll get the same thing on only 2 cores. I've now removed the buffering and the ordering again, that's why we see random results here. Okay, but that's now with degree of parallelism. So you can customize this in easy ways, and the magic is just in LINQ. Every iQueryable in LINQ, which also means every iEnumerable, can be converted into a parallel processing task just by using as parallel. Does this mean that this is safe, or that you can forget about doing, lock statements in between? Well, no, not at all, because this code will execute multi-threaded, and if you access global state, for example, you still have to lock this. You have to do regular, safe, programming in here, multi-threaded programming. That's dangerous. That's really dangerous because this code like this, looks like functional programming code. And in a pure functional language, code like this would be safe. This means you would not have to take any kind of locking into account. Why? Because in a pure functional language, you would not have a side effect onto a global variable. But right now we do have side effects, so we need to lock. Because this thing runs on multiple cores at the same time. If you have a single core machine today, or if you have a single core hyperthreading machine which simulates 2 cores, then you have to be careful because these machines cannot actually represent the kind of multi-threading issues you will run into. If you do multi-threading development today, you need to get a real multi-core machine, not a single core hyperthreaded machine. That's very, very important because you want, in a single core machine, you will never run into a concurrent resource access situation or into a cache coherence situation just because they don't exist. You only have one cache. If you run a single core hyper-threaded CPU, you have one cache. So your cache cannot become inconsistent. So you don't need to lock. If you run the same code on a dual core machine, on a real dual core machine, you will have side effects here, which you did not intend. That's important. So you can, if you run on single core hyper-threaded today, you can go to your boss and tell them that I told them or told you to tell them to get you a new machine. No, really. I mean, you need this. If you do multi-threaded programming, you need real multiple cores. The best you can get is real multiple processors, 2 CPUs, because they are even further apart. They share less. The less they share, the more problems you will see in reality, the more issues will come up. And these issues are issues which your customers will see. I will see these issues because I run 4 real cores on my machine. Okay. So the next one that's an interesting one. No, I deleted too much. No, I didn't delete too much. This is a find operation now. I'm sorry. This is a first or default. Now, this is something where I'm looking for the first item which fulfills a certain criteria. In my case, I still run the process method, and if it's greater than 500, I want to have this particular item. And let me run this. And the thing is, that's pretty interesting. It looks for the first item. It doesn't look for any item in this sequence. It looks for the first item. And in here, it realizes that, these items, they can't match, so it immediately stops processing these. And instead, it does new work splitting. It moves the thread which processed this item, and lets it start here to process items in this direction instead. So let's just see this again. And well, it's too fast. The problem is this takes a while. The whole reallocation of threads and rechecking of items takes a while. The system will scale up the number of threads if it notices that it's possible, but right now there are too few items, and it takes about 1 or 2 seconds for the scheduler to adapt to your real load. Okay, but that's important. Again, it tests, and if it can't fulfill this, then it exits threads, exit prematurely. You don't have to synchronize this again. Next is number 13. Oops, no, I can't this one. Can't do this. And number 13 is parallel aggregates. It's not just that you can run things in parallel, you can aggregate things in parallel. So now that's the regular link-based aggregation list.sum of process. If you run this quite quickly, this just iterates over all the things, sums up the results, everything's easy, no question, and we should get a result, and the result is some arbitrary value which has been returned from my process method. And if we want to do aggregates, we can also do this by just running as parallel. You can run your aggregates as parallel aggregates as well. And let's just start this. So we're running this in parallel, aggregation is done in parallel, but of course we get the same result. So that's also possible. That's just for completeness sake. That's nothing magic. You would have expected this by now anyway, that this is possible. Okay, the next one is, task of int. Now I need to change the sequence of my demos because the task of int is a little bit late. I should have moved this earlier, now that I think about it, and because we talked about this before. That's the piece of code I typed manually before. Okay, so let's go back and run the next one instead, because the next one will be more interesting. Everything you've seen so far was based on the tasks framework or parallel link or parallel dot for each. Well, actually, there's one more thing which I'd like to show you. There is a parallel dot invoke, not just parallel for each, but parallel dot invoke. That's pretty interesting. It allows you to just specify a number of Lambda expressions, a number of actions, and run them in parallel. So I could do Lambda 1 is messagebox.show foo. Lambda 2 is messagebox.show bar. And if after this is completed, I can do a messagebox.show completed. This will now run these two tasks in parallel. It will wait for both of them to complete and will then, of course, just continue regularly. So let's just run this. And I get my two message boxes, foo and bar. Just regular message boxes, the first two tasks. As soon as both complete, my application will continue to run. That's just an imperative statement, just parallel.invoke. If you don't want to deal with that whole tasks infrastructure, you can just invoke any number of tasks in this way. And so we have three things. We have parallel link, and we have the task framework. And we have one more thing. If you need to have more control over your system, more control over how certain items are processed, etc. And if parallel link is not enough, then you can create your own consumer or your own creator-consumer pattern or implementation. And that's now a regular thing. That's partly what you would have done in the past before the parallel framework. Now, we have done a number of projects which had to do work similar to what the TPL allows us to do in a very easy way today. They had to parallelize things. And normally when you parallelize things, you need to put them onto a work queue. And you will have one or more readers which read from this queue. Now, the thing is, this queue has to be synchronized. So you have 10 readers waiting for items to end up in the queue. And if your queue is empty, they have to block. Now, a producer puts something into a queue, and a monitor will be triggered. Some kind of synchronization construct will be triggered so that it wakes up a listener, so that the listener can take this item and process it and wait for the next item to end up in the queue. And then you need to synchronize the end of the queue. So your producer has to be able to say, you know what, I'm done. And as soon as the producer says, I'm done, the consumers will read the queue up to the point where it's empty, and then the consumers will exit, because then they know that there's no more work for us to do. And the blocking collection is one of those collections in system collections concurrent, which allows you to do things like this. There are more. You have things like a concurrent queue and a concurrent stack, etc., things which are just thread-safe collections. And then you have the blocking collection, which allows you to do cross-thread synchronization, not just cross-thread blocking, but also synchronization. Okay, and if you want to do manual dispatch, what you can do now is you can say, well, you know what, I want to have a new blocking collection. It should allow a maximum of 1,000 items to be n-queued. After 1,000 items, my producer has to block. As soon as there are 1,000 items in the queue and my producer wants to put an additional item in the queue, the producer will block, and it will only continue after one of the consumers has taken an item out of the queue. Why is this important? Well, otherwise you can end up with memory explosion. If you, let's say, read messages from I don't know, an MSM queue, a Microsoft messaging queue, and you get loads of messages, you take them into memory, and your producer puts tasks into this, or, well, not puts work items, not tasks, because a task is a special keyword, as you've known, puts things into this queue, then the queue could explode if the consumers are not fast enough. So you can limit this one here. Then I'll start worker processes or worker threads, and every thread executes this worker thread proc, and that's how your worker thread procedures would look like. So you have your work items blocking queue, and as long as this queue has not been completed, you call work items.take, and then you process the item. So that's the loop, that's the logic behind this system. And to put items into the queue after starting the workers, you will, or in my case, I just iterate over this data set, over the 1,000 items, and I call work items.add, I put my things into the queue, and after this I call complete adding. And after completing the adding process, the workers will just know that they have to exit. So if you run code like this, we can specify the number of workers to start. I'm starting with, let's start with 4 workers for now. And let's run this. So we now have 4 workers. They are now not doing any kind of locality optimization magic, because it's my queue now. And in my queue, I enqueue things from the top, and it's real first in, first out queue. But you can see I have 4 concurrent readers on this. There are 4 different blocks which are read right now. And if I go to the maximum of my CPU, I run 8 readers, then you will see that the items are processed in a faster way and using more than 1 or more than 4 readers. But this is manual optimizations. Now I have to know how many threads I want to use, how many concurrent cores I want to use concurrently, etc., etc. Okay, so let me just check. We've done all, yeah. Okay, so let me switch back to the slide deck. I'm just glancing over this pretty quickly with you. It's a reference deck, as I said, so I think we should have covered everything. That's the task API. We definitely use the task API. There are different ways you could start a task. So I like the Lambda syntax. If you don't like the Lambda syntax, you don't have to use it. You can just pass a method name of an existing method, or you can use the delegate syntax if you prefer this for whatever reason. And then you can call wait or wait all, wait any. We talked about this one. Okay. If you have a task of int, then you can process the int as a result. This will block until the task has finished. To continue tasks, you can use continue with. You've seen this one. You create the first task, and then I let this task continue with another task. Then you can pass in options. So we have seen this one. We have seen the debugger, where you can get some kind of overview over your system. We haven't seen the parallel stacks. That's another window in Visual Studio, which allows you to see multiple stacks at the same time. So that's, let me just zoom in a bit. It's read from the bottom to the top, and it shows you call stacks which are similar. If you have a multi-threaded application, no matter if it uses the tasks framework or classic multi-threading, you can see how the structure of the application came to be. So you have call stacks which are similar. So here we have, for example, 3 threads which have this call stack. And after this, from these 3, we have 2 additional threads which have this call stack. And you have 1 thread which is currently executing in this thread. So you have the other thread here is still blocking at this method. That's why it didn't go any further. But so you get a graphical view of all these threads. Of course, everything here is clickable. You can click an item and you'll get to the source line. This is parallel stacks. You get this in debug Windows parallel stacks. You've seen parallel.invoke. We've seen parallel.forEach at the beginning, where you can pass in a list and a delegate, or a list and a lambda expression to execute on each item. We've definitely seen sParallel and all the options. Oops, I'm being a bit too fast. All these options which you have, buffering, degree of parallelism, and ordering. You have this unified cancellation using cancellation token cancellation source. We've seen that one. And we've seen the blocking collection just right now at the end. And that's on the API level. On the conceptual level, there are a handful of things which might be interesting. If you create your manual system based on a blocking queue, what's happening is your blocking queue is actually being read by multiple cores or multiple threads at the same time. Now the problem is, and that's a low-level optimization. It's an optimization which is very hard to do manually. And well, it's not impossible, of course, but it's just hard to program this. Now, if I have 8 cores, for example, and I have 8 execution threads which read from one queue, they will block quite often, because they will block whenever they go to the queue. They first, there has to be a lock in between, so because I can't modify the queue from multiple items at the same time. Now, so what the system does behind the scenes is it uses one queue for each core instead of one massive shared queue, because the shared queue wouldn't work as nicely. So it uses one queue per core. But if let's say the first core runs empty, it does work stealing. It goes to another queue, it looks at the other cores, and then does a lock operation. It moves items over to its own queue. Then again, it can read without any locks from its own queue. You get this locality by last in, first out optimization for the last one. So these are just the conceptual things. And maybe that's, just as a summary, what we've seen is task, we've seen parallel.invoke, parallel for each, and link as parallel. What we have not yet seen is what the future brings. Some of you might have seen this in previous session by Bartel Smith. We just talked about this, and he said that he has shown this. In the future, and this is currently available as a CTP, which you can download and run on top of your existing Visual Studio or .NET version. But in reality, this is going to be part of the next .NET Framework version. And these are 2 new keywords. There is one keyword which is called async and one which is called await. And what happens here is, and this is pure magic. For those of you who have not been at the previous session, this is magic. This method is an asynchronous method. Well, I indicate this using the async. And the await keyword creates this asynchronous task and the delegate, etc., behind the scenes. So the await basically takes whatever is coming after it and moves this into a task. And it returns immediately, this method returns immediately and returns the task. And that's magic. You don't have to create tasks anymore. You can just say async and await. Now, what happens if you have more than one await like this? Let's say, oops, that's not as nicely as I wanted it. So we have await, task, delay, return 7, but here we could have, await, task, delay, something, and then, do something which would be called synchronously, and then we'd have await task.delay. Of course, this wouldn't be a task delay, but this would be some other task. You're waiting on something, and then we return it. And this would now internally automatically be converted into 2 different tasks. So you'd have one task which does this thing and internally starts the second task which does this. And that's a related task, and you'll just get reference to your one task, to the one you can call .result on to get your result. That's massive. That's magic. You know, and the problem with parallel programming is that it needs to be easier. Because if it's not easy enough, then we won't use it. And if we won't use it, this means that people will spend a lot of money to get a 128 core machine, and you will never use it. We will never utilize it as developers. So what if you are in the position today to create applications which do processing and data processing in your application, which do CPU-bound operations, not I/O-bound, but CPU-bound, then you should think about parallelism. And what you get today using parallel, using p-link, and using task is pretty massive compared to what we had before. And as soon as you add the future or await and async to it, you can see that a lot more APIs, internal APIs, will be developed in an asynchronous way. And that's something I'm hoping for, because otherwise we will never be able to take advantage of these big core machines. And I'm promising you one thing. Today my notebook has 8 cores. But if I come back in 10 years to this conference, it will have 128 or more cores. And we need to realize this. In 10 years, my phone will have 32 cores. And that's quite impressive. So if we don't take this into account, we will never be able to utilize any kind of advances which are going to come. And with this, I'd like to thank you for being here. I hope that you've enjoyed the last 75-ish minutes around parallel programming. I hope that I didn't scare you off too much with my predictions. But really, I believe that we are running into 32 core phones in 10 years. And we need to take this into account. Thank you very much for being here.